I enjoy programming, but I do not enjoy complexity. That's why I code in the terminal in C. That said, when it comes to graphics, OpenGL is a pain. SFML is okay, but it didn't really tickle my fancy. So when I stumbled across Raylib 4.0 new stuff video in my YouTube feed, I was intrigued. And pretty soon after looking into it, excited. After doing some basic examples, I was sold. I've studied a decent bit of electrical engineering and physics, both fields heavily steeped in waves and mathematical models of waves. If you heard waves, and this is what came to mind. Here's some background. Those are waves, but that's a huge system with a lot of drivers and a lot of reducing factors that make the system super complex and almost impossible to model. We don't like complexity in our models. Thankfully, we can very often take a simple case, understand that, and then apply it, either through expansion or orthogonality, to larger, more complex cases. Roughly speaking, a wave is the propagation of some stimulus through a medium, originating at a source and spreading outward. Well, if you studied quantum, you'll argue with that, but that's a discussion for some other time. I can think of two basic examples. One, you grab a string at one end and shake it side to side, and you can see that your stimulus, the shaking, spreads out along the length of the string. I imagine you did this experiment sometime in elementary school. Another example is to take a basin of water and kind of poke it at a fixed interval in one place. You can see the ripples moving outward. You can even tap it in two places and watch the ripples from each interfere. Anyway, the math is governed by this equation. The derivations of this are actually quite interesting, but beyond the scope of this video. I'm just going to use this, which is a basic sinusoidal stimulus propagating in one direction. For the most part, I'll hold time constant and just look at spatial effects. Furthermore, I can apply this to two dimensions by calculating y, x, and t along a radial vector. I started off with a simple example, just one source frozen in time. This code creates an image and a texture to hold the wave information. I have some inputs in the main loop to move the source around and modify some of the parameters. Then I have a big loop that just goes through each pixel, calculates the distance to the origin, then passes that information through that sine equation I showed earlier. The output data is written to the image as a pixel color, and the texture is updated and drawn to the screen. I should note that each pixel is calculated separately. The inputs for each calculation are independent of all other calculations. This means that, in this example, and for much of my code in this video, you can probably convert it into a shader and run it more efficiently on the GPU. I say probably because I don't know how to do that. Anyways, running this code gives me pretty standard output, which is nice, but kind of gives me a headache. That's a pretty boring example, but it serves as a basis for the next step, which is to expand the simulation to encompass multiple sources. So for starters, I replaced the single speaker position, vector 2, with an array that will allow for some maximum amount of emitters, and a count variable to keep track of how many emitters there actually are. I wanted to encode this information into an image, so I actually write these to an image as a green pixel and then re-extract them, just for fun. In order to calculate all the active emitters, I just need to add a for loop around the WaveGen image loops. I can also play the image by stepping the time parameter in the sine function. A quick side note, the colors that represent the amplitude scale from 0 to 254, which are the values that each pixel in the image can hold. I need to scale each individual emitter's contribution to the waveforms by the number of emitters. So in the case of a maximum superposition, the combined amplitudes is either 254 or 0. This is pretty simple. I can just set the amplitude to be the max amplitude of negative 127 divided by the count, which is the number of emitters. The base case here is the same, but with a lot more interesting functionality. I can increase the number of emitters like so, and you can see the interference patterns they generate. I can also randomly generate new positions, which is fun, though I messed up my indexing, so some of them aren't in frame. What's really cool is I can play the simulation, and you can watch as the waves propagate. Honestly, it's so much cooler to watch because I made it myself. Also, here's the obligatory two-source interference pattern. Fun stuff. Now comes the difficult bit. I want to generate these, but passing through objects of different densities and, consequently, different propagation speeds for the wave. And the math for this becomes a lot more complicated and breaks down into brute forcing it for each medium and then putting it all together in the end. After mulling over it a bit, I figured I could just cast arrays out from the source and track a normalized distance to use in my little sine function. I created an obstacle texture that had the density encoded into it, scribbled out a pseudo-mathematical justification, then wrote a bunch of code to track the ray and update its direction when it encountered a new background using Snell's law. It's kind of ugly, but here's the result. It looks nifty, but it's not behaving correctly. The incoming ray is perpendicular to the surface, so it should always pass straight through the interface. First off, I wasn't using Snell's law properly, so I had to add an asine call. Then I capped the argument to between -1 and +1. And that worked at first, until it didn't. What was going on here? Why is it making this 90-degree turn after leaving the material? I mean, rays sometimes do that, but only at the critical angle. And this was orthogonal. Speaking of critical angle, I shouldn't be capping the argument's value if it's out of bounds for a sine, because then it should be reflected, right? Right? Wait. After stepping away and collecting myself, I collected my stuff and started fixing the code. I fixed the critical angle checks and added the reflection calculation, but I realized I had made a fundamental error with the Snell's law calculation. The theta used for that calculation was actually the angle I was using in code to represent the ray's global direction. Snell's law uses the angle between the incident ray and the tangent line to the surface. I fixed this by encoding the normal vector into the obstacle image and then adding these calculations to the code. This seems like it's working. The ray gets stuck inside, but I think that's okay. I'll figure it out later. I wanted to make sure this worked against the base case I showed earlier. So I got rid of all the obstacles and I set the ray to just increment around one single emitter. Uh-oh. For reference, this is what it should look like. Figuring it was some issue with rounding on the path length calculation, I played around with that for a while, varying parameters to see if I could get any noteworthy results. Here are the outputs for the different step sizes. 0.1, 0.25, 0.5, 0.75, 1, 1.5, 2, 5. Anyway, after a short break, I went back to the code and realized that the ray propagated only when the sim was playing. And when the sim was playing, I was advancing time while calculating a single frame. I commented that out, and everything started working properly. So I cleaned up and reorganized all the code, then expanded the simulation to two sources the same way I did for my initial simulations, and lo and behold, it worked, generating a diffraction pattern. Next, I really wanted to add the obstacles back in and get that working, but I've spent far too long on this already. I'm not sure this technique will pan out in the end. I'll probably have to go back to my initial idea or maybe play around with using Fermat's principle to back calculate the ray path for each pixel. Either way, I could use some distance from this problem. For now, here's the broken object attempt that I threw together.